Namaskar and welcome to another round of discussion on concrete engineering and technology, and this module seeks to revise basic principles underlying concrete science and engineering, develop a framework which helps us understand the present day scenario in concrete engineering with developments in admixtures, methods of construction, different materials being used and so on, and going through some of the issues which are of special relevance in special and high performance concretes and their quality control and testing, including performance based thinking, durability and maintenance. Now, once we are talking about fundamentals of concrete, we have talked a little bit about pores and porosity in concrete arising out of hydration in cement. And at that time, we have talked about origin of pores and porosity, we have talked about the nature and characterization of pores in terms of the total pore volume, the differential pore volumes and so on. And we have also talked about measurement of porosity in concrete using mercury intrusion porosimetry. Now, of course, mercury intrusion porosimetry is just one of the tools, but we have an idea of the fact that concrete is a porous material having pores of different sizes, and those pores can be measured. Where those pores come from is primarily on account of water added to concretes being far in excess of that required for hydration of the cement. Chemically, that water being about 18 to 22, 23%, and the actual water being added being in the range of 40 to 55% in most cases. A lot of water does remain behind in concrete after the hydration has taken place, and this is the kind of picture that we showed, showing cement and water before hydration, during hydration and at the end of the hydration process, where in this particular case we have shown no cement is remaining, and all the cement has been converted to hydration products. And this is the total amount of pores that are formed within concrete. Whether they are saturated with water or not is a different story, but yes, this is the amount of space which is available for water to be present, and if water is driven out, leaves, that is the amount of space which is left as pores as far as concrete is concerned. We had looked at this picture, which is a representation of aggregates surrounded by cement paste matrix, and this matrix having pores. And then we had seen a reiteration of the definition of porosity, which is nothing but a measure of the void space in a material, that is, it is a fraction of the volume of voids to the total volume, and can be expressed in terms of cc per cc or cc per gram of the material and as a percentage and so on. The question that we now start to deal with is that of porosity versus permeability. Porosity, as we have discussed, is the intrinsic property of the material measured in terms of the amount of void space as a percentage of the total volume. So, porosity is an intrinsic property of the material. We can say that, okay, here is a material which is porous, which has a certain amount of total voids. We can talk in terms of the pore size distribution of that material, but at the end of it, it is a property of the material. Permeability, on the other hand, is the ease with which something can navigate through the pores of the material. Thus, in addition to the porosity per se, because obviously a material from outside can navigate through the pore system only if there are pores. If there is no pores, then we are not talking of any navigation, or we are not talking of any permeability. The fact that we are talking of permeability means that there is a material which has some pores. But in addition to the porosity, there are other things that govern the ease with which a material from outside can travel through that material. and this depends on factors such as the pressure of application, properties of the material and so on. So, for example, if there is water, in certain cases water can flow very easily. If we apply pressure, it flows more easily. The ease being defined in terms of or measured in terms of, for example, the velocity of flow or the quantity of material that flows per unit area, per unit time and so on. If instead of water we have another fluid, then the permeability changes. If we are talking of gases or air moving through the porous medium, the concept of permeability needs to be defined in terms of gaseous permeability. And all this discussion is true even for concrete. Water moves through concrete, so we can talk in terms of water permeability of concrete. Gases such as carbon dioxide, oxygen, they move through concrete, they enter concrete if it is dry. Therefore, the concepts of gaseous diffusion in concrete is equally valid. There is ionic diffusion, chlorides from outside, for example, in a marine environment, they move into the concrete pores. So, we have ionic diffusion, the ionic permeability. All these concepts of diffusion and permeability are applicable as far as concrete is concerned as well. We have talked about measurement of porosity, and today the discussion would focus on permeability. Permeability is measured in units of length per time. We talk of centimeter per second or meter per second, and we are familiar with the discussion of Darcy's law that helps us understand the flow of water through soils. In concrete, the porosity and interconnectivity of pores in the cement paste and micro cracks, especially at the paste aggregate interface, plays a very important role. We talked about this when we were talking about porosity. These in turn, that is the porosity and the interconnectivity, depend upon parameters such as the water cement ratio, the degree of hydration, degree of compaction and the quantity and characteristics of the constituent materials, that is cement, sand and so on. Before we get started with our discussion on permeability, let us look at these two graphs, which are the result of an experimental study which talks of air permeability index. So, there is something called an air permeability index. If concrete has pores, there is a thought at least that we can understand that yes, if it has pores, air will be able to permeate through those pores. And if we are able to have a test which will measure the air permeability of a concrete, that should be somehow related to the water cement ratio of that concrete, because that really determines the porosity of the concrete. So, if we look at these points that have been obtained here, we see that there is a lot of scatter, but at the end of it, the basic trend that as the water cement ratio is higher, the air permeability index is higher, that does not seem to be violated, except that of course, depending on the age and the mix of the concrete and so on, those numbers actually could be different. What is interesting is this graph here. If we look at a plot of compressive strength versus permeable voids, and if we look at this range here in the range of let us say 30 to 50 MPa of compressive strength of concrete, the permeable voids percentage varies within a fairly large range. What this tells us is that even though we say that the strength is related to the water cement ratio, and we put forward an argument which says that okay, if the water cement ratio increases, the total pore space increases, and therefore the strength goes down, because the strength is related to the pore spaces through an equation of this nature. All this understanding becomes very suspect, because we have evidence that the amount of permeable pores varies quite a lot at a given water cement ratio, or for the same permeable pores the strength range is fairly large. What this tells us at the end of the day is that if we are doing performance based thinking, then permeability needs to be considered, at least for the time being, almost an independent criteria for evaluating concrete. Most of our thought process till date is governed by the fact that concrete is characterized by a principal parameter called compressive strength, and so long as compressive strength is under control, we have a concrete which meets compressive strength requirements, all is well. What this kind of a diagram shows us is that as far as durability is concerned, because durability is primarily related to the movement of deleterious ions through the pore structures of concrete, as far as durability is concerned, we perhaps need to establish permeability as an independent criteria for characterizing the performance of a concrete. We can talk of measurement of permeability as a parameter for quality control. That is what we talked about just now when we said that, well, permeability should be used or can be used as an independent criteria for establishing and characterizing concrete mixes, or there can be a situation where we are talking about measuring in situ permeability as part of non-destructive testing and evaluation of a structure, in addition to normal tests which give us results in terms of compressive strength, ultrasonic pulse velocity, cracking and so on. We can talk in terms of measuring permeability of concrete in situ in the structure. Now, out of these two, the discussion today would focus on measuring permeability as a parameter for quality control. That is, we will be primarily talking about some tests which have been proposed and developed in the last say 20, 25, 30 years, and establish permeability as a characteristic of concrete, independent of compressive strength. One of the tests that comes to mind in this context is the AASHTO, the American Association for State and Highway Transport Officials, their test standard called T277, or the ASTM C1202, which is a rapid chloride permeability test. Now, this, as the name suggests, is a method for measuring the chloride permeability of concrete. The test basically consists of testing a water saturated 50 mm thick, 90 to 100 mm diameter concrete specimen subjected to 60 volts of applied DC voltage for 6 hours using an apparatus specially designed for the purpose. One reservoir, that is on one side we have a reservoir which has 3% sodium chloride solution, and in the other reservoir we have 0.3 m NaOH solution. Now, chloride permeability is one of the most important parameters that an engineer who is concerned with durability of concrete in marine environment or durability of concrete on account of likely corrosion of reinforcement due to chloride ingress is concerned about. So, we want to establish how soon or what will be the level of chloride permeability in concrete, and this is one of the tests. These pictures here, they show the test method as is actually used. This here is the test setup as is used, and this is actually a schematic representation. This is the concrete disc, and we apply a voltage of 60 volts across the two faces of concrete. one phase of the concrete is in contact with 0.3 and sodium hydroxide solution, and the other phase is in contact with the 3% sodium chloride solution. And what we really try to do is to induce the chlorides to move through the concrete, except that the measurement is not in terms of movement of chlorides, but it is the current that flows on account of application of this 60 volts across the two faces. And this current is actually measured over a period of 6 hours, and we calculate the total charge that has passed. This picture here is a setup of a commercially available setup, where several of such cells can be tested together. So, we can put in several specimens of concrete and run the test in a manner that we can get the current values for each of these channels and try to get the Coulomb values or the charge which has passed for the different specimens. What is really done at the end of it is the total charge passed is determined, because the charge that is passed is related to the current. It is only the integral of the current over time for the whole of 6 hours, and this is measured in coulombs. So, once we have the I and T data, that how much of current is flowing through the two faces or through the concrete over a period of 6 hours at periodic intervals, we can convert it and obtain the total charge that has passed, and that has been qualitatively related to the permeability of concrete. It is not a quantitative relationship, it is a qualitative relationship, and says that if the charge passed is more than 4000 coulombs, the chloride permeability is high. If it is 2000 and if it is between 2000 and 4000, it is moderate. If it is between 1000 and 2000, it is low. If it is between 100, if it is between 100 and 1000, it is very low, and if it is less than 100, it is negligible. What a user, as far as performance based thought process is concerned, could do is to say that, well, I want a concrete to be used in this structure which has such and such strength as far as structural design is concerned, but I want the concrete to have not more than moderate chloride ion permeability as determined by the ASTM C1202 test. So, now we have established an independent criteria for evaluating the concrete or the suitability of a concrete that is going to be used in a structure. Apart from the strength criteria, which is coming from the structural design, there is a durability criteria which is coming from the point of view of chloride permeability, defined in terms of the rapid chloride permeability test, and a specific number or a specific target is given that it should not be more than moderate. This test obviously has certain limitations. The current passed is related to the ionic conductivity of the pore solution, which is related to its ionic composition. What is happening in this test is that at the end of it, this is the concrete piece or the specimen, and we are applying a charge which causes this current to flow through the concrete. So, even though we are trying to measure the current, what we are effectively trying to do is to determine the resistance of the concrete and how it changes over time, because once the resistance changes, the current also changes. Now, once this is the mechanics of the test, what we are really concerned about is that the ionic composition of the pore solution, what kind of ions are present, that would have some bearing on the ease with which the current can flow through this concrete. The measurements are made before steady state migration is achieved. So, it is not a steady state measurement. We put the apparatus together, switch on the equipment and start measurements right away for a period of say 6 hours. So, it is not a steady state measurement, The voltage applied tends to increase the temperature. So, as I said, the test is basically of conductivity of the concrete and its correlation with chloride ion permeability. Thus, any conducting material present in the sample will create a bias in the test and causing the results to be higher. So, if there is more conductivity, the I will be higher, that is the current will be higher, and therefore, we will get results which would indicate that the coulombs are higher. Another variation from the rapid chloride permeability test is the so called salt ponding test, which has been standardized in AASHTO T259. The previous one was AASHTO T277. Now, in this test, what is done is that 3 slabs having a certain area, having a certain minimum thickness, they are moist cured for 14 days, stored in a drying room at 50% relative humidity for 28 days, and after this a 3% sodium chloride solution is ponded on the top surface for a period of 90 days, while the bottom face is left exposed to the drying environment. The slabs are removed from the drying environment and the concentration of chlorides in thick slices or in slices is determined. So, if you look at the diagrammatic representation of this test, what it does is, we have a concrete sample which is sealed on the sides, is exposed to a 50% relative humidity atmosphere at this end, ponded with 3% sodium chloride solution on the other, and we have the sodium chloride solution permeating into the concrete. And at the end of the 90-day period, we try to take a core out of this concrete specimen, cut that into slices and determine the chloride concentration in the different slices. So, in this slice, which is the closest to the surface, the concentrations are going to be higher, and as we go deeper into the concrete, the concentrations will go down. So, effectively what we try to do is to try to determine what is the chloride ion concentration and how it varies with depth. That is, we take slices from the surface inside and measure the chloride concentration. These chloride concentrations can be measured by powdering the concrete, extracting the chlorides into an acid or a water solution, and then carrying out a normal titration or an ion selective electrode method. And finally, the evaluation on the basis of T259 is based on the chloride concentration in a given disc or a diffusion coefficient which can be estimated based on this distribution that we get based on this profile. It is easy to understand that if a concrete has the distribution which is shown in green here compared to another concrete which has chloride concentrations like this, the red concrete has more porosity or a higher chloride permeability compared to the concrete which gives us the distribution that is shown in green. So, basically through a ponding test, what we try to do is actually measure the chloride concentrations that are achieved within a concrete slab at the end of the 90-day or a 3-month exposure period. The limitations of this test obviously are, it is a complicated testing condition and the crudeness of the evaluation. The testing conditions are complicated because even the specimen preparation and the pre-treatment is quite complicated. Preparation of the slab, moist curing, dry curing at 50% RH for 28 days, and then having the concrete dry at one end, saturated with a sodium chloride solution on the other, promoting or driving the sodium chloride solution into concrete on account of this gradient arising out of the dry weather or the dry environment in this side of the concrete slab. It is quite a complicated testing condition. the salt ponding test does provide a crude one dimensional chloride ingress profile, but this profile is not just a function of the chloride diffusion. And since the specimens have been left to dry for 28 days, there is an initial sorption effect when the slabs are first exposed to the solution. Because there is a drying involved, because the specimens that are used in the test are initially dry, so it is not only the chloride ions that move in, but also the water that moves into the concrete, and that complicates the behavior, and that complicates any modeling that a scientist or an engineer might like to do for this test. So, all this contributes to the complicated testing conditions, and at the end of it we need to wait for a period of 90 days before we can actually pronounce a judgment as to whether or not a concrete is acceptable. Of course, the merit of this test is the fact that it is close to the actual exposure conditions of concrete. At least in marine environment, we can say that yes, the concrete is going to be subjected to salt water or immersed in salt water in certain cases, and we would like to know how much of salt water would penetrate. We would like to predict that, but how much we can predict on the basis of a 90-day test compared to the service life of a structure, which could be several tens of years, that is a different question altogether. Thus, as far as the 259 and the 277 are concerned, both of them give us results as far as chloride permeability is concerned. In one case, the results are available in let us say about 6 to 10 hours, because the actual test in 277 is for 6 hours, and if we give or take a couple of more hours for preparation and so on, the results are available very quickly. But in the case of 259, the results are available only after a period of 3 months. Continuing the discussion on chloride permeability, there is a bulk diffusion test called the NOD test NT build 443, and this test is basically similar to the salt ponding test, except that instead of being dried for 28 days, the test specimen is saturated with lime water to prevent any initial sorption effect, and also instead of coating just the sides of the sample and leaving one face exposed to air, the only face left uncovered is the one exposed to 2.8 m NaCl. So, instead of a 3% NaCl solution, we use a 2.8 m NaCl solution in this case, and the period of exposure is at least 35 days. So, we can read more about the details of this test, but this is a representation of how the test is actually carried out. So, as against 259, where this space was open, and part of the reason for driving the chlorides into the concrete was the drying that was occurring on this face. In this case here, the specimen is saturated with lime water to get rid of the sorption effects initially, and also ensure that the movement of chloride occurs only on account of diffusion. Initially, the pore solution will be free of any chloride ions. Once it is exposed to the 2.8 m NaCl, the chloride ions would begin to move into the concrete, and again we would get a chloride profile which would look like something like this. So, at the surface we will have a large amount of chlorides. As we go deeper into the specimen, the concentrations would become smaller. If we want to compare the chloride concentrations in this test with respect to those obtained in the 259, it is difficult to say, but on the face of it, it can be said that they are likely to be lower, for the simple reason that the period of exposure here is lower. We are just talking for 35-day test compared to the 90-day ponding there, plus the fact that in the 259 we were driving the chlorides into the concrete along with water by having an evaporation or the drying of concrete at the other face, which is not happening here. In this case, of course, we talk in terms of the acid soluble and the water soluble chloride ion content, and the engineers can decide what kind of a specification they want to write. It can be said that, well, we want a concrete when tested with this standard should not have an acid soluble chloride content at a particular depth exceeding a certain number. We can write a specification which says that the total chlorides at x is equal to 10 mm should not exceed some number. Another engineer could say, I would like to have a concrete where the soluble chlorides at x is equal to 15 mm should not exceed a certain number. So, this is what we want to state by saying that we are getting into performance based specifications. We are not talking only in terms of the strength of concrete, but also in terms of the actual chloride permeability of concrete. Now, what I wanted to point out with this slide was really the fact that these tests, some of them are as recent or as old, whichever way you look at it, from 1991 and so on, which means that we are looking at tests which have been developed in just about the last 20-25 years. And that means that they have a short history, and some of these tests are still in the research stage, some of them are being practiced. Apart from the novelty of this test, let us continue with our discussion on some other forms of chloride permeability testing. And here we have the pressure penetration technique, where the chloride solution is pushed into the concrete under pressure, and the concrete specimen is drawn out and sprayed with silver nitrate solution, and we get a white deposit in areas where the chlorides have penetrated. So, in a manner of speaking, this test is similar to that we carry out when we measure the carbonation depth. Of course, in that case what we are trying to do is measure what areas the calcium hydroxide has been lost by spraying phenolphthalein. In this case, we are trying to measure the areas where chlorides have reached within the concrete, and we do that by spraying a solution of silver nitrate, and silver nitrate in the presence of chloride becomes silver chloride, and that is the white deposit or the white precipitate that we see. So, well, it is not easy to have a unique value of this depth, because the profile of this white color will not be very regular. There will be aggregates within which will distort the profile further, but that is what an engineer has to decide, how to arrive at some kind of a measure of average depth of chloride penetration at the end of the test. Obviously, things such as the specimen preparation, the chloride concentration, the load to be applied, the duration for which it is to be applied, and so on, that have all to be standardized in this kind of testing. So, in principle, what we have is a lot of methods use a setup which is summarized here. We have a concrete specimen. On one side we have a chloride rich environment, on the other side we have a environment which is not having chlorides to begin with, and then we try to push the chlorides through the concrete onto the other side. Now, if we apply a direct current here, the test becomes similar to, or the test basically becomes the T277, that is a rapid chloride permeability test. If we do not apply any current externally, it becomes a pure diffusion cell kind of a setup, where we have to wait for the chlorides to emerge onto the other side before we can talk in terms of the permeability or the chloride permeability of this concrete in between. When we are trying to do diffusion cell kind of a setup without accelerating the chloride movement, obviously the test could go on for a very long time, unless we are able to reduce the thickness of the concrete which we are testing. If we are able to get a very thin slice of concrete, yes, then we can try to have results very quickly. But the problem of creating that thin slice of concrete for a test like this would be in terms of creating or generating or causing cracks in the concrete, and therefore, that is a very, very severe limitation in terms of the applicability of a pure diffusion cell kind of a test. Of course, using these ports here, we could use a reference electrode and just dip the electrode here at different points in time, maybe after a month, another month, and so on, and try to see whether or not the chlorides have reached the other end or this chamber here, or what is the concentration. And once we know the concentration of chlorides in that chamber and we know the volume of the water or whatever we are using in that chamber, we know the area of the concrete through which the chlorides are diffusing, the time that is taking, and the thickness of the concrete sample. This information is enough for us to be able to estimate or calculate the permeability of concrete or the chloride permeability of concrete. Now, with this kind of discussion on chloride permeability of concrete specimens or concrete, let us move towards the permeability of concrete for other materials such as water or gases. The liquid permeability, water is generally of interest to us. We measure it in two ways. One is by the rate of inflow or outflow, and the other is by a depth of penetration at a given time or in a given time. We will talk about these two tests a little bit in the next slide and so on. They help us establish or estimate the coefficient of permeability of the concrete based on either the Darcy's equation or the Valentin equation from the depth of penetration. Now, let us see what the water permeability of concrete, the so called output method or the constant head method means. It means that first of all, the method is suited for concretes which are highly permeable. That is, a concrete sample which is placed like this and water is put here and a pressure is applied, water actually flows out from the other side of the concrete sample, and we can collect a certain reasonable amount of water in a reasonable time frame. The test is carried out using a disc of concrete and involves water flowing through it at a steady rate. And to accelerate the process, of course, pressure can be applied, but the pressure to be applied is limited by the fact that concrete cannot be subjected to bending, because the moment the concrete bends and being weak at tension, the concrete will simply break. We do not want the concrete to break. We want only the water to move through the concrete and not causing any flexure cracks in the concrete. So, the pressure applied has to be limited from that consideration, and it should be borne in mind that the disc cannot be made too thin. The permeability of concrete being essentially low, the experiments could take a fairly long time. To address this, we often carry out the test using the depth of penetration method. In this case, what we do is that basically a modification of the above test and is carried out using larger specimens, and water is applied at pressure at one end. That does not change. What happens is that after a fixed time interval, the specimens are split open and the depth of water penetration is observed. So, we have a concrete cylinder or a concrete specimen here, we apply water pressure on this, and at the end of a certain fixed time split the cylinder and try to see how much is the depth of penetration of water. And this depth of penetration of water again is not so easy to measure because of reasons arising from practical considerations in terms of the presence of aggregates, the non-regularity of the pore structure, and so on. At times, if this sealing here at the edges is not very properly done, it is likely that the water can move along the edges and penetrate into the concrete from the sides, in which case instead of getting a profile like the one that is shown here, we may get a profile which is something like this, and this water coming from the sides, and that is something which is highly undesirable as far as this test is concerned. So, observing all these precautions, if we are able to carry out this test, yes, the depth of penetration is representative of the water permeability of the concrete that we are testing. There are some recommendations which allow us also to estimate the actual permeability in terms of units such as the centimeters per second or meters per second, based on this height h, or the depth of penetration of water at a certain pressure that occurs over a certain period of time. This here is the test for sorptivity of concrete. That is a relatively new test, which where a concrete specimen which is 100 mm in diameter, 50 mm thick, is exposed to water with a filter paper wrapped on it, and at selected intervals ranging from 1 to 25 minutes. The sample is removed from water and the stopwatch is stopped. So, we are watching or we are measuring the penetration of water or the absorption of water by this specimen in a matter of minutes, and this excess water is blotted off with a damp paper towel, and the sample is weighed and put back in the shallow pan of water for the experiment to be continued. And what we record is the gain in mass per unit area over the density of water. This, if it is plotted with the square root of elapsed time, the slope of this line gives us the sorptivity value. So, we really obtain the volume of water absorbed divided by the area of the specimen, and if we plot it with respect to the root of time, we get a constant or a straight line, and the slope of which is reported as the sorptivity value. So, basically what we are saying is that we are looking for a measure of water absorption in the concrete, and this test can be completed fairly quickly, except for the time that is required to prepare the specimen in the first place. I must refer you to this document, which is largely the basis of our discussion today for water permeability as well as chloride permeability of concretes. Now, before we close, let us try to think of some questions that we want to take home. We could collect data relating to different parameters related to concrete permeability. We could use compressive strength as the base parameter. We could try to get sorptivity values as reported in the literature with different concretes. We could get RCPT values, we could get values from the T259 kind of tests and so on, and try to see how they are related with each other. We could make a list of the standard tests for measurement of chloride and water permeability. Of course, we have mentioned some of the tests in this discussion today, but there are a lot of others, and I think that if you are motivated enough and interested in the subject, you would look up the literature and come up with several other tests. We could find out if there are any performance based specifications for concrete that may be used in a structure on the basis of chloride or water permeability, like the examples that we talked about when we were discussing the results from T277 or T259 and so on. Like chloride ion water permeability, can we talk in terms of oxygen or nitrogen permeability of concrete? That is a question that I would leave with you to ponder about. Thank you. Before we close the discussion, let me show you a diffusion cell kind of a setup, which can obviously be modified to carry out a test in accordance with ASTM C1202 or AASHTO 277. This is one of the cells or one of the reservoirs with a hollow space here, which can be filled with either sodium hydroxide or water or a chloride solution. this is a wire mesh which is used to apply current if the concrete is being placed in between the two reservoirs like this. So, we have two reservoirs on either side of concrete. There is a concrete block in between measuring about 90 to 100 mm diameter, 50 mm thick, and held together using bolts and so on. If we want to apply current, we can use wire meshes like this to apply the current. The assembled cell looks something like this. We have a reservoir on one end, we have a reservoir on the other. There is a concrete disc in between, and the whole thing is held together with bolts. So, if we want to regularly sample whether the chlorides are coming on to the other side or not, whether they are traversing the concrete thickness or through the concrete or not, or what is the rate at which they are doing that, we can always have probes through these holes that are there on the reservoirs. As far as T277 kind of tests are concerned, we can use these wires which are connected to the meshes that we saw to impress a certain amount of current across the two faces of concrete.